Welcome! Today, we'll dive into the problem number 692 titled Top K Frequent Words. In this problem, we'll explore how to identify the most frequently occurring words in a given text and rank them based on frequency and lexicographical order. Let's get started. In this problem, you are given an array of strings called words and an integer k. The goal is to determine the k most frequent words from the array. The output must meet two criteria. First, the words should be ordered by their frequency in descending order, meaning the most frequent words come first. Second, if two words have the same frequency, they should be ordered alphabetically in ascending order. For example, if two words each occur twice, the one that is alphabetically earlier should appear first. The input includes a list of strings, where the length of the list is between 1 and 10,000, and each string consists of lowercase English letters with a maximum length of 10. The integer k will always be at least 1 and at most the number of unique words in the array. The output should be a list of the k most frequent words that adhere to the specified sorting rules. Let's consider the first example. The input array is words equals I, love, LeetCode, I, love, coding, and k equals 2. The task here is to find the two most frequent words. When we count the occurrences, the word I appears 2 times, love also appears 2 times, while LeetCode and coding each appear once. Among the words with the highest frequency, I and love both occur twice. To determine their order, we use alphabetical sorting, so I comes before love. As a result, the output for this example is I, love. Now, let's look at another example. Here, the input is words equals the day is sunny, the sunny is, and k equals 4. This means we need to find the 4 most frequent words. Counting the occurrences, the appears 4 times, is appears 3 times, sunny appears 2 times, and day appears once. Sorting by frequency, we get the order, the is, sunny, and day. Since there are no frequency ties that require alphabetical sorting here, the output is simply the is, sunny, day. Let's analyze a third example where the input is words equals A, AAA, and k equals 1. Here, all the words occur exactly once. Since their frequencies are tied, we rely on alphabetical order to determine the result. Among A, AA, and AAA, the word comes first alphabetically. Therefore, the output is A. This demonstrates how ties in frequency are resolved consistently by sorting the words alphabetically. Finally, let's examine some edge cases. If the array words contains a single word repeated multiple times, the result will simply be that word repeated k times. For instance, if words equals hello, 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 and k equals 1, the output is hello. Another important scenario is when multiple words have the same frequency and need to be ordered alphabetically. For example, if words equals B, A, C, B, C, C, and k equals 2, the word C appears 3 times, and B appears 2 times. Since both words have unique frequencies, we don't need alphabetical sorting here, and the output is C, B. These examples highlight how the constraints and rules ensure a clear and consistent solution, even in edge cases. To begin tackling the problem of finding the top k frequent words, the brute force approach gives us a straightforward starting point. The idea is to first count the frequency of each word using a dictionary. Once we have these frequencies, we can sort the dictionary entries by 2 criteria, the frequency of the words, which comes first, and their lexicographical order as a secondary criterion. After sorting, we simply return the top k words from the sorted list. However, a key observation here is that sorting all the words, including those we don't need, can be computationally expensive. This sorting step alone has a complexity of n log n, where n is the number of unique words. So, while this approach is simple to implement, it becomes inefficient for large datasets due to the unnecessary overhead of sorting everything. The overall time complexity is n log n, and the space complexity is n, due to storing the frequency dictionary. Now, we can improve upon this by using an optimized approach based on a min heap. This method allows us to focus only on the top k frequent words, avoiding the need to sort the entire list. First, we count the frequencies of all words using a dictionary, which takes n. Then, as we iterate through the dictionary, we push each word frequency pair into a min heap. If the heap size exceeds k at any point, we remove the smallest element, ensuring that the heap always contains exactly the k most frequent words. Once all words are processed, the heap will hold the desired results. At the end, we extract and sort these words if needed, based on frequency and lexicographical order. The key advantage of this approach is that the heap operations, both push and pop, take O log k, making it much more efficient than full sorting. The overall time complexity becomes O n log k, while the space complexity involves O n for the dictionary and O k for the heap. While this method is more efficient, it does require understanding and managing a heap, which adds a layer of implementation complexity. Another efficient alternative is the bucket sort approach, which groups words based on their frequency. First, we count the frequencies of all words using a dictionary, which takes O n. Next, we create a list of buckets where each index corresponds to a frequency, and each bucket contains words with that specific frequency. By iterating through the buckets in reverse order, starting from the highest frequency, we collect words until we have selected k of them. If needed, these selected words can then be sorted lexicographically as the final step. One key observation here is that this approach avoids explicitly sorting all words, as we only traverse the buckets. Importantly, the size of the bucket list is determined by the maximum frequency, which is often much smaller than the total number of words. This makes the method highly efficient, with a time complexity of O n plus k log k, where the final sorting step depends on k. The space complexity is O n, due to the dictionary and the buckets. While this approach is efficient and well-suited for cases where the frequency range is small, it can be less intuitive to implement compared to the heap-based approach. After evaluating the different strategies, we chose the optimized min-heap approach as the preferred solution. This method strikes a balance between efficiency and simplicity. With a time complexity of O n log k, it is well suited for handling larger datasets, scaling efficiently with input sizes up to the problem's constraints, such as 10 to the power of 4 words. Additionally, the implementation is relatively straightforward, leveraging standard library functions for heap operations. Compared to the bucket sort approach, it avoids the need to explicitly manage buckets, which can be less intuitive. While the brute force method is conceptually simpler, its O n log n complexity makes it less practical for larger inputs. The heap-based approach ensures that we only process the top k elements and maintains the desired order efficiently. In summary, this strategy offers an optimal trade-off between performance, clarity, and ease of implementation, making it the ideal choice for solving this problem. In this problem, we are tasked with finding the top k most frequent words from a given list of words. If two words have the same frequency, the word that comes first in lexicographical order should be prioritized. To solve this, we start by parsing the input, which consists of a list of words and an integer k. For example, if the input is words equals apple, banana, orange, banana, and k equals 2, our goal is to identify the two most frequent words from the list. The first step in our algorithm is counting the frequency of each word. This can be done using a dictionary, where the key is the word and the value is the frequency of that word. For instance, the resulting dictionary from our example input would be apple, 2, banana, 3, orange, 1. A dictionary is ideal here because it allows efficient insertion and lookup operations, ensuring that we can count word occurrences in just 1 time on average for each word. This forms the foundation for the subsequent steps of the algorithm. Now that we have the frequency of each word stored in a dictionary, the next step is to sort the words based on their frequencies in lexicographical order. To achieve this, we first convert the dictionary into a list of tuples, where each tuple represents a word and its frequency. For example, the dictionary, apple, 2, banana, 3, orange, 1, becomes apple, 2, banana, 3, orange, 1. Sorting is then performed with two conditions: words with higher frequency should come first, and for words with the same frequency, the one that is lexicographically smaller should come first. In Python, this can be implemented using a sorting function like sorted, frequency.items, key equals lambda x, x1, x0. Applying this to our example, the sorted list becomes banana, 3, apple, 2, orange, 1. Sorting ensures that the words are arranged in the desired order, and from here, we can easily extract the top k elements. Although the sorting step has a time complexity of O n log n, it simplifies the problem significantly, as we can directly retrieve the top k words from the sorted list. After sorting the words, the next step is to extract the top k words from the sorted list. This is straightforward, we simply take the first k elements from the list. For our example, where k equals 2, the first two words in the sorted list, banana, 3, apple, 2, orange, 1, are banana and apple. Thus, the result is banana, apple. This list is returned as the final output. A few key insights about the algorithm can be highlighted here. First, using a dictionary for frequency counting is efficient because of its O(1) average time operations. Second, the custom sorting function allows us to handle both frequency and lexicographical criteria seamlessly. However, sorting is the most computationally expensive step, with a complexity of O(n) log n. While alternative approaches like heaps can reduce this complexity, they might introduce additional implementation complexity. Overall, our approach strikes a balance between simplicity and efficiency, making it a solid choice for this problem. To analyze the algorithm's complexity, we break it down into three main steps. First, frequency counting has a time complexity of O(n), where n is the total number of words in the input. Second, sorting the list of unique words requires O(m) log m, where m is the number of unique words, and since m is always less than or equal to n, this step dominates the overall complexity. Finally, extracting the top k words is an O(k) operation. Combining these, the total time complexity becomes O(n) plus m log m. In terms of space complexity, the dictionary used for storing word frequencies requires O(m) space, and the sorted list also takes O(m) space. Thus, the overall space complexity is O(m). It's also important to consider edge cases. For instance, if k is greater than the number of unique words, we simply return all unique words sorted by frequency and lexicographical order. If all words have the same frequency, we rely on the lexicographical sorting to determine the result. Finally, for an empty input, the output is naturally an empty list, as there are no words to process. Let's walk through an example to solidify our understanding. Given the input words equals apple, banana, orange, banana, and k equals 2, we start by counting the frequencies of the words. This yields the dictionary, apple, 2, banana, 3, orange, 1. Next, we sort these words based on frequency in lexicographical order, resulting in the sorted list, banana, 3, apple, 2, orange, 1. From this list, we extract the top k words, which are banana and apple. Finally, we return the result as banana, apple. This example demonstrates how each step of the algorithm works in practice, from frequency counting to sorting to selecting the top k words. By following this structured process, we can reliably solve the problem for any valid input. This implementation solves LeetCode problem number 692, top k frequent words using Python. The goal is to find the k most frequent words from an input list, prioritizing lexicographical order when frequencies are tied. ###explanation line by line. Step 1 *. The counter from the collections module counts the frequency of each word in the input list. This creates a dictionary-like structure where the keys are words and the values are their respective frequencies. For example, given words equals apple, banana, apple, the frequency map would be apple, 2, banana, 1. Step 2 *. A min heap is used to maintain the top k frequent words. Each entry in the heap is stored as a tuple, count, word. The negative count ensures that the heap organizes by highest frequency instead of the default smallest value. Additionally, Python's heap automatically resolves ties by comparing the second value, word, lexicographically. For example, pushing apple, 2, and banana, 1 results in heap equals -2, apple, -1, banana. Step 3 *. To retrieve the top k frequent words, the heap is popped k times, extracting the word component of each tuple. This ensures the result list contains the k most frequent words in order of priority. For example, if k equals 2, popping the heap twice extracts apple, banana. ### edge case is handled. If k equals the number of unique words, all words are returned. If multiple words have the same frequency, lexicographical order is used to break ties. Works efficiently for large inputs due to the O(n) log k complexity. This complete implementation is efficient and adheres to the constraints of the problem. Here, we start by importing the necessary Java utilities and defining a class called solution with a method named topkFrequent. The goal of this method is to find the k most frequent words from the input array. First, we create a frequency map using a hash map. This map will store each word as a key and its corresponding count as the value. To populate the map, we iterate over the input array and use the getWordDefault method to increment the count for each word. Once we have the frequency map, we move on to the next step, which is to maintain the top k frequent words using a priority queue, implemented as a min heap. The comparator for the heap sorts words first by their frequency in ascending order. If two words have the same frequency, they are sorted lexicographically in reverse order, meaning lexicographically larger words will come first. This ensures that when the heap exceeds size k, the least frequent or lexicographically larger word is removed. We then iterate over the frequency map's keys, adding each word to the heap and removing the least desirable element when the heap size exceeds k. Now that the heap contains the top k frequent words, we move on to extracting these elements to form the result. We do this by repeatedly pulling words from the heap and adding them to a list. Since the priority queue ensures that the least frequent words are removed first, the words in the list will currently be in ascending order of frequency. To correct this, we reverse the list using the collections.reverse method, so the words are arranged in descending order of frequency, which matches the problem's requirements. Finally, we return this list as the result. This completes the implementation, effectively leveraging a frequency map and a priority queue to solve the problem efficiently. In this problem, we are tasked with finding the top k most frequent words from a given list of words. The result should be ordered such that words with the highest frequency come first, and if two words have the same frequency, they should be sorted alphabetically. Take the example where the input words are I, love, LeetCode, I, love, coding, and k is 2. The first step is to count the frequency of each word. Using Python's counter, we get a dictionary where the keys are the words and the values are their frequencies. I appears twice, love appears twice, while LeetCode and coding each appear once. Next, we utilize a min heap to help us track the top k frequent words. For each word frequency pair, we push a tuple containing the negative of the frequency and the word into the heap. This ensures that higher frequencies are treated as smaller values, allowing us to retrieve the most frequent words efficiently. If two words share the same frequency, the heap will order them alphabetically because strings are naturally compared lexicographically in Python. As we build the heap, let's look at the intermediate states. After pushing the pair for the word I with a frequency of 2, the heap contains one element, -2, I. Then, we add love, which also has a frequency of 2, and the heap becomes -2, I, -2, love. Adding LeetCode with a frequency of 1 updates the heap to -2, I, -2, love, -1, LeetCode. Finally, after adding coding with a frequency of 1, the heap holds -2, I, -2, love, -1, LeetCode, -1, coding. Once the heap is fully constructed, we proceed to extract the top k words. This involves popping from the heap k times. The first pop removes I, leaving us with a heap of -2, love, -1, coding, -1, LeetCode, and our result array contains I. The second pop removes love, resulting in -1, coding, -1, LeetCode, and a final result of I, love. Thus, the output for this example is I, love. Now, let's examine a second example where the input words are the day is sunny, the sunny is, and k is 4. First, we calculate the frequencies of each word. The appears 4 times, is appears 3 times, sunny appears 2 times, and day appears once. With these frequencies, we proceed to build the heap. After pushing the pair for the heap contains -4, the. Adding is with a frequency of 3 updates the heap to -4, the -3 is. Next, sunny is added, creating a heap of -4, the -3 is -2, sunny. Finally, day is added, and the heap becomes -4, the -3 is -2, sunny, -1, day. To extract the top 4 words, we pop from the heap 4 times. The first pop removes the, leaving -3 is -1, day, -2, sunny, and a result of the. The second pop removes is, leaving -2, sunny, -1, day, and a result of the is. The third pop removes sunny, and the fourth removes day, resulting in that it is sunny, day as the output. Finally, consider a third example where the input words are a, B, C, and K is 1. First, we calculate the frequencies. The words A and B each appear twice, while C appears once. Using these frequencies, we build the heap. After pushing the pair for A, the heap contains -2 A. Adding B updates the heap to -2 A, -2 B. Finally, adding C results in -2 A, -2 B, -1 C. Since we only need the top one word, we pop the heap once. This removes A, leaving -2 B, -1 C, and our result is A. Thus, the output for this example is A. To analyze the time complexity of solving the top k frequent words problem, we can break it into 3 key steps. First, we count the frequency of each word in the input list using the counter class from Python's collections module. This step involves iterating through all n words in the list, making it an O(n) operation. Next, we build a min heap to store the negative frequency and the corresponding word for each unique word in the frequency dictionary. Since there are m unique words, and each heap push operation takes O log m, this step requires O m asterisk log m time. Finally, to extract the k most frequent words, we perform k heap pop operations, each costing O log m. In total, extracting these elements takes O k asterisk log m time. These 3 steps together form the foundation of our time complexity analysis. When we look at the overall time complexity, the dominating factor depends on the relationship between n, the total number of words, m, the number of unique words, and k, the number of results we want. Step 1 takes O, n, Step 2 takes O, m asterisk log m, and Step 3 takes O, k asterisk log m. Since the number of unique words m is at most equal to n in the worst case, we can simplify the time complexity. If k is small, the overall complexity becomes O, n plus m asterisk log m, which further simplifies to O, n asterisk log n in the worst case. Shifting to space complexity, we analyze the memory requirements. First, the frequency dictionary stores the count of each unique word, which takes O, m, space. Then, the heap structure stores up to m elements, also requiring O, m, space. Finally, the result list for the top k words takes O, k, space. Together, these components define the memory usage of the algorithm. Now, considering the overall space complexity, we sum up the space required for the frequency dictionary, the heap, and the result list. This leads to a total of O, m plus k, space. Since m is at most equal to n, the overall space complexity simplifies to O, n plus k, in the worst case. Comparing this to a brute force approach, a naive solution would count word frequencies, sort all unique words by their frequency in lexicographical order, and then return the top k words. This would have a time complexity of O, n plus m asterisk log m, similar to the optimized approach. However, the heap-based method is more efficient in terms of memory, as it avoids sorting all m words when only k results are needed. By focusing on only the most relevant elements, the heap ensures that we minimize unnecessary operations, making the algorithm both time-efficient and space-efficient. Breaking down the time complexity further, we can analyze the best, average, and worst cases. In the best-case scenario, when k is very small and the number of unique words m is much smaller than n, the heap operations are relatively inexpensive, and the overall complexity approaches O, n. In the average case, for typical input sizes where m is proportional to n and k is small, the complexity is O, n plus m asterisk log m. Finally, in the worst case, where all words are unique, meaning m equals n, and k is large, the complexity reaches O, n asterisk log n. This breakdown highlights how the algorithm adapts to different input conditions, maintaining its efficiency across a variety of scenarios. When solving this problem, there are several common mistakes that can lead to incorrect or inefficient solutions. One of the most frequent errors is not accounting for secondary sorting. For instance, when 2 words have the same frequency, the problem often specifies that the words should be sorted lexicographically. Overlooking this can lead to wrong output. To fix this, you can use a stable sorting method or explicitly sort by frequency in descending order and lexicographically in ascending order. Another mistake is implementing an inefficient sorting strategy. Sorting the entire list of words without considering that you only need the top k most frequent words unnecessarily increases the time complexity. Instead, a heap-based approach allows you to extract the top k elements in O, n log k, which is more efficient than sorting the full list in O, n log n. Finally, incorrect frequency calculation is another common pitfall. Errors such as forgetting to initialize a word count or accidentally overwriting existing counts can lead to logical mistakes. To mitigate this, you can use Python's collections, counter, or similar tools to manage frequency computations accurately and efficiently. Another common issue arises from overlooking edge cases. For example, failing to handle situations like empty input, a single word input, or cases where all words have the same frequency can cause runtime errors or incorrect outputs. To address this, make sure to thoroughly test your solution with edge cases such as empty strings, very large inputs, and ties in frequency. Additionally, some solutions ignore the constraints or input size specified in the problem. Writing a brute force solution without considering these constraints can result in your solution exceeding time limits, especially with constraints like 1 equals k equals n equals 10 to the power of 5. To avoid this, ensure your approach scales efficiently as input size increases. Efficient algorithms, such as those leveraging heaps, are a good choice for handling large inputs. In interviews, solving top K problems effectively often comes down to pattern recognition. Many of these problems involve a combination of hash maps to calculate frequencies and heaps to extract the most frequent elements. Recognizing this pattern can streamline your thought process and help you arrive at a solution faster. It's also important to understand trade-offs between different approaches. For example, be ready to explain why you chose a heap over sorting and to discuss their respective time complexities, O, n log k, for heap-based solutions versus O, n log n, for sorting. If the interviewer asks for an optimized solution, focus on reducing redundant computations, such as avoiding the unnecessary sorting of the entire list when you only need the top k elements. Additionally, clarifying requirements with your interviewer is essential. For example, ask whether the input contains duplicates or how ties in frequency should be resolved. This not only ensures your solution aligns with the problem requirements but also demonstrates your ability to approach problems thoroughly and methodically. There are several related problems on LeetCode that share similarities with top K frequent words. For instance, LeetCode 692 focuses on frequency and lexicographical order, just like this problem. LeetCode 347, top K frequent elements, is similar in terms of extracting the top K elements but doesn't involve lexicographical sorting. LeetCode 451, sort characters by frequency, shifts the focus to sorting characters instead of words. Finally, LeetCode 973, K closest points to origin, relates to the top K pattern, but here the key is sorting based on distances rather than frequencies. Now, in terms of alternative approaches, using a heap-based method is a popular choice. This approach keeps track of the top K frequent elements efficiently and is particularly useful when K is small compared to n. However, it requires careful implementation to manage memory efficiently. Another option is bucket sort, where words are grouped by frequency into buckets, and you iterate over the buckets from highest to lowest frequency. This method is often space efficient but can feel less intuitive, especially for beginners. Finally, another alternative approach worth discussing is quick select. This technique adapts the partitioning method from quicksort to find the K most frequent elements. It's particularly fast on average, with a time complexity of O, n, making it a great choice for scenarios where performance is critical. However, it's important to be aware of its trade-offs. If the pivot is poorly chosen, quick select can degrade to O, n squared, in the worst case. While this is rare in practice, it's something to keep in mind when considering this approach. Overall, quick select can be a powerful tool, but it requires a solid understanding of partitioning logic and careful implementation to avoid pitfalls. Great job! In summary, we tackled the top K frequent words problem using hash maps and heaps for an efficient solution. We also discussed time and space complexities and key takeaways for solving similar problems. If you enjoyed this, make sure to check out more problems and keep practicing. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!